Okay, so welcome to today's Tutte colloquium. We are very happy to have um, Jordan Ellenberg here as speaker. So Jordan Ellenberg is the John MacArthur Professor of Mathematics at the University of Wisconsin-Madison. So his research centers on number theory and arithmetic geometry with connections to topology, combinatorics, and data science. So he's also the author of the general audience book, How Not to Be Wrong, The Power of Mathematical Thinking, and The Forthcoming Shape. So I was actually reading something, if you are interested, to read some of the descriptions of his like interesting story of his early life and his careers as nonfiction writer in Wikipedia. But today we are going to focus on math. So welcome, Jordan, to talk about Beyond Rank.
Thanks so much, and it's a pleasure to be back in Waterloo. I've been to Kitchener once before, and I hope someday to come again in person. So I want to talk about this. Is actually a new talk. So I put together some stuff I've talked about before, but in a different combination. So I'll be interested to hear how it goes. Just about these general notions that go beyond the popular notion of rank from linear algebra. But before I start, I do want to start. I hope not on too much of a down note, but I just want to sort of send best wishes to the family of, unfortunately, Louis Solomon, my colleague at Wisconsin, my emeritus colleague, just passed away. I just heard, who was a pioneer, as many of you know, in the study of hyperplane arrangements. And that interplay between geometry and combinatorics, which is so beautifully realized in that subject and in the theory of the Orlik-Solomon algebra, and et cetera, et cetera. So let's dedicate this talk to him today, because I will try to speak in that spirit of the interplay between algebra, especially linear algebra, and combinatorics that Lewis was such a master of. So as I wrote these notes, I realized that it takes a little saying to talk about what aspects of rank I want to go beyond. So let's start by talking about rank, and there will actually be like quite a few things to say, and let's see how we go, because I want this talk to be accessible to everyone. So let me remind you the rank of a matrix, and there's a lot of different ways to express what this is. So I'm going to tell you some of them, because we're going to kind of think about all of them. Probably the way you learn it in a linear algebra class as an undergraduate is that it's the dimension of the space spanned by the columns of a matrix, right? So for instance, a rank 0 matrix is one where there's no choice. All the columns have to be 0 because they span a 0-dimensional space. A rank 1 matrix, let's look at this one, would be, if you look carefully at the columns, you see that that they're all multiples of each other. So there's 3 columns, but there are 3 different points in the same line. So they span a 1-dimensional space. By the way, that constrains the rows to also span a 1-dimensional space, which would be yet another characterization of the rank that I'm not going to talk about. And then here, the identity matrix, here the columns are just a basis for the 3-dimensional space. So they span the full 3-dimensional space. That's the maximum the rank can be, since of course the columns are vectors in R3. And this is in some sense the generic case, right? If I write down a random matrix with a very high probability, its rank is going to be full. Its rank is going to be n if it's an n by n matrix. Well, that probability is 1 if I'm over the real numbers or complex numbers. Over a finite field, boy, that's another beautiful story that I'm not going to tell in today's talk about probabilistic questions like that. So let's talk about some equivalent characterizations. To have full rank, and I'm only going to talk about, I think I'm only going to talk about square matrices today. Oh, that's not true. I am a little bit later going to talk about rectangular matrices. Well, for an n by n matrix, where this notion makes sense, to have full rank and the largest possible is the same thing as saying that the matrix is non-singular, because the columns span everything. That means that thought of as a linear transformation, the map is surjective. So rank captures this notion of singularity versus non-singularity from a matrix. Another way to say that is that a matrix is, of course, non-singular if it has no 0 eigenvalues. And indeed, the rank, another way to think of it, is it's just the number of non-zero eigenvalues. If you like list all the eigenvalues in a row, some of them are 0 and some of them are not. And the number which are non-zero is the rank. And of course, you have to count with multiplicity, right? Whenever I say the eigenvalues, I mean that there's a double eigenvalue counts twice. Okay, so just this sort of philosophy here, which we'll return to, is that the rank sort of captures features of a matrix we care about, like what its eigenvalues are, how non-singular it is, etc. And although I didn't really justify this in this slide, it's easy to compute. I mean, you can write down a very big matrix and compute its rank like really fast. Like those are sort of linear algebra operations that we can just do. Let me say, because as a true algebraist, I don't like to think about, well, I do like to think about matrices, but one is supposed to say one doesn't like to think about matrices. We like to think about linear transformations of an abstract vector space. So if instead of saying a matrix, I just say I have a vector space which I have not chosen a basis for, and just say A from V to V is a linear transformation, then the rank of A is the dimension of the image of that transformation. So if it's the zero transformation, it has zero dimension. That's the smallest possible. If it's an isomorphism, it has full image. Its image is all of V, and the rank is as big as possible. So I think a good way to think about what rank is, to have in mind as we sort of move beyond it, is it's an answer to a question of like, how zero is it? So here's it's like literally zero. That's the smallest a rank can be, and the least zero a matrix can be is if it's non-singular, if it's an invertible matrix. One way of thinking of it is that for numbers, I'm teaching graduate algebra this term, so this is like on my mind. In a field, an element is either zero or it's invertible. There's no in between. And with matrices, we have this kind of added richness that there's sort of degrees of non-invertibility measured by the rank. How far are we on the scale from here to here? Okay, I'm going to say yet more about what rank means, because there's so many different ways to express it. First of all, what does it mean for a matrix to be rank 1? So another way to say it, literally, I was just teaching this when I talked about tensor products in algebra this morning, is that it can be written, and I made a mistake. It's the other way around, right? Now this is cool because now we're in iPad land. I can just fix it on the spot under our, yes, that's the way I want it. So let's actually see this happen so we can see this matrix. So for instance, this matrix that I wrote here would be, so e.g., I already forgot it, and the amount of time it took me to, that's the column vector 1, 2, 3 times the row vector 1, 2, 4. So the entries of that matrix, the ij entry is just the ith thing of this times the j thing of that, and that gives you this rank 1 matrix that I drew. So a rank 1 matrix is a matrix that can be expressed as one vector times another vector transpose. And now here's another definition of rank. A rank R matrix is just something which can be expressed as a sum of R rank 1 matrices. This is, I want to say this is like linear algebra 101, but it's more like linear algebra 102. It's more like one of these very useful facts that somehow in a typical undergrad linear algebra course, I think we don't usually teach. But this is yet another characterization of rank. And so I'll just comment, maybe sort of speak to computability. Well, actually, this refers to something. I may or may not say something about this as we go, but to comment that a rank R matrix is very easy to compute with. So usually if I want to multiply a matrix by a vector, I'm going to have to do a bunch of multiplications, right? I got to compute n dot products, and each dot product requires me to do n multiplications. That's n squared multiplications in all. If I have a rank R matrix, I could do that. I could use all n squared matrix entries of the matrix, but I could do it in only Rn multiplications because, in some sense, you should think of this as like a compression of the matrix, right? I'm sort of specifying only R times n numbers and telling you what the matrix is that way. And so it's a more efficient representation of the matrix. And if there's time, there may not be, I'll say something in the beyond rank section about sort of what these notions of low rank have to do with computability. Okay. So that's your sort of whirlwind tour of the basics of the notion of rank of a matrix. Now I'm going to talk about a couple of applications of rank, which may be a little bit less familiar, who knows? And then I'll take those applications and sort of see how they generalize beyond rank. Okay, so here's an application. Ready? You all know like kind of Math Olympiad type problems where somebody tells you a sequence of numbers and then they're like, what's the next number? Okay, this is kind of like that. I'm going to give you, instead of a sequence, I'm going to give you a matrix with an element missing, and you got to fill in the missing number. Now, how are you supposed to do that, right? I mean, any number could be an entry of this matrix. But there is sort of a best answer, at least under some philosophy. And this is sometimes called the Netflix problem. And let me explain why. I'm going to write a little bit on here. You could think of a matrix like this as a matrix of users and movies. So maybe there's like user 1, user 2, and user 3. And maybe these are like 3 movies, like, I don't know, like Dumbo. Now I'm going to think of 3 movies. I probably should have done this in advance, right? Metropolitan and Star Wars. And we've got to predict, let's say we actually know how each user rated each movie, except we don't know whether user 2 liked Dumbo or not, and we've got to predict. Well, maybe what we can glean from the entries that we already have is that maybe if these numbers represent degree of approval. Now, in reality, as you guys know, if you use Netflix, you're only allowed to put like 1 through 5 stars. So I'm already giving you a little more data. But let's suppose we were on a sort of 12-star Netflix system. It kind of looks like Star Wars is the best of these 3 movies, right? In general, people rate it higher. And it kind of looks like user 3 is the most positive of these 3 users. And user 1 is like the least positive. Like basically every time user 3 and user 1 rated the same movie, user 3 rated it a lot higher. In fact, rated it 4 times higher. So in a very simple model, you might say, okay, well, Star Wars is a better movie than Metropolitan, is better than Dumbo. And user 3 just fundamentally likes movies more than user 2, more than user 1. And so what should user 2's rating for Dumbo be? Probably somewhere in between user 3's rating and user 1's rating, which are 4 and 1. And also, it should probably be less than user 2 thought of Metropolitan and Star Wars because Dumbo is the worst of the 3. And indeed, probably a good thing to put in here is something like 2, because that sort of corresponds well with the information we've already seen about how people rated movies. And of course, what we're really doing here is positing, so here's the philosophy, that matrices in the real world like to be low rank. So really the way you could describe what I did here is to say, it's a problem called low rank completion. I had a matrix with some missing entries, in this case, just 1. And tried to fill it in a way that the resulting matrix has low rank. And this is a very beautiful question, actually, that a lot of ink has been spilled about in the world of machine learning and data science. It's now, I think this particular problem, I would say, is now pretty well understood how to do it. And I'll emphasize that Netflix actually used this. I mean, this is actually how recommender systems often work, using some tricked out version of this idea. And maybe, okay, I can't resist saying this is a slight digression, but literally just this week, and I want to recommend this, I found a cool game on my iPad called I Love Hue, which is basically low rank completion, but for colors. It doesn't say it's about low rank completion, but it's this kind of fun game I was playing with my daughter, where you're basically trying to complete a rank 1 matrix where instead of numbers, you have like colors of varying shades. So just a comment, a news you can use. Okay, so if you believe the matrices you find in the real world tend to be low rank, this gives you a great way to either fill in missed data, or if you have inaccurately measured data, like data with some noise, maybe you have low rank matrix approximation, where maybe I have all the numbers in here. Maybe instead of a blank, maybe I had, 1.7. And I was saying, well, I'm not confident of this number, or maybe any of the numbers, and I want to find numbers that are nearby where the matrix is low rank. Very similar problem, also huge amount of papers on it, also pretty well understood at this point. Okay, so that's one application. Let me talk about a totally different one in geometric combinatorics, namely the problem of few distance sets. Okay, what does that mean? So an S distance set in Euclidean space, although actually it'd be fun to do this in metric spaces. I'm not sure what's been done, but we're going to talk about Euclidean space today. It's a subset, a set of S, a finite set S of points in space, so that if I look at the distances between every pair, now I'm going to get about whatever the size of S is, about the square of that, that many distances, and I want all those numbers to take only S values. That's a very strong condition. It seems like it's probably hard to make an S that's big, that has that property, but let's try to figure out how big. This is a very traditional Erdos style, shall we say, problem in extremal geometric combinatorics. So for instance, a one distance set, what does that mean? That means that literally any 2 points in your set, any 2 distinct points, did I say that? Oh, I should have said distinct pairs of points, sorry. Because I certainly don't want to count 0. Any 2 distinct points are at the same distance. And actually that means it has to be a simplex, right? So here's a one distance set in Rn. And you probably know, or if you don't know, can convince yourself that I can't do any better than this. If I have k points, which are all supposed to be equidistant from each other, every pair has the same distance, like a regular k simplex, I need k minus 1 dimensions to do it. I can have an equilateral triangle in R2, but I can't have like an equi-square. I can have a regular square, but the diagonal points are far apart, right? I can't have a square, I can't have a quadrilateral where every 2 points are equidistant from another. If I have 4 points with that property, it has to pop up and be a regular tetrahedron, and it needs to be in R3. So, okay, ready? Here's a theorem that is not so hard to prove, that a one distance set in Rn, the biggest it can be is size n+1, and it's a regular n simplex. Okay, so far so good. What about a 2 distance set? Already now, this is like a harder problem. Can anybody visualize? Okay, so a 1 distance set in R2, the biggest it can be is an equilateral triangle. Anybody want to yell out? Can anybody think of this is like good? This is like a combinatorics and optimization talk. So I'll give you one optimization problem. Now I'm giving you a combinatorics problem. And I'll give you a hint. I already told you a 2 distance set. I already told you 1 2 distance set in R2. Can you think? Come on, somebody else. A regular pentagon? A regular pentagon. I love it. There it is. You made my next slide. There it is. A regular pentagon. There's only 2 possible distances. And in fact, this is the biggest possible. So I'll leave that as sort of a fun combinatorial exercise. That you cannot put 6 points in R2 in such a way that they only delineate 2 distances. And here's a wonderful theorem of Blockhouse, which I didn't write down the date, but it's the 80s. It's not that long ago. That a 2 distance set in Rn has size at most n+2 choose 2, or half n+1 n+2. And by the way, already we're talking about some open problems because there is a lower bound that is also on order 1/2 n squared, but it's smaller than this. And we actually really don't know like exactly how sharp this is. So there's a range, and I think as of now, I was just looking this up this week, there are only finitely many n where we provably know the exact optimum. We have a pretty decently small range. It's between this and like 1/2 n squared or something like that. But we don't actually know exactly how big a 2 distance set can be. So let me show you. I'm not going to quite prove. Oh my God, I spelled Blockhouse's name wrong. Sorry, he does not have a C. So let me show you a quick and dirty way to prove essentially this theorem using ideas about rank, because this kind of gives the ideas that we're going to imitate as we go past rank. And actually, this is essentially Blockhouse's proof. He doesn't quite write it this way, but this is essentially what he does, and it can be massaged to give exactly this bound. I'm going to be sort of soft about constants. So yeah, what does this have to do with rank? Seems like I totally switched gears and I'm talking about like extreme combinatorics, which I love to talk about, but this talk is about rank. So let me explain what it has to do with rank. Okay, ready? So suppose my 2 distance set. That's 2 different distances. Let's call them beta. And aim to the size of my sets. Okay. All right. Ready? I'm going to make a matrix. The matrix could be distance between x and x. I'm giving those this is an m by m matrix.